start button, as it were?
Just get
There you
started.
go.
Yeah. Let me share my screen. Second here. You see it?
Yes.
Okay. Good. All right. So welcome to Data Science Learning Community, Deep Learning for Coders, Part 2. We are on lesson 17, which covers initialization and a little bit of optimization. This was based on a video, right? This one was longer than some of the other ones. It's closer to 2 hours. And the overarching goal here was we're working on the fashion MNIST data set. If I could spell here. And the idea is we want to get close to 90% accuracy on the validation set. And I think I actually hit 90% on one of my, randomly initialized models, but we get close nonetheless with these variants that we look at here. Before I go into this, I don't know if you guys ran into this problem. This is the notebook number 11 from part 2. And when I load the data set, or when I had initially this data loaders from DD, I was getting an error message, and it was saying something about it didn't know what this get DLS function was. Did anyone run these notebooks? And this is something that would have come up in the last couple weeks as well. This would have been a problem last week.
I haven't.
Um,
I have been running the notebooks, so to speak, and then I'm kind of
okay.
copying them into my own notebook and adding my own notes. But I didn't run into that issue. It should be that should be in the data sets thing. Import star from data sets. That's where that should be defined.
Yeah, so I traced out the issue. So like Torin, for instance, if you have problems, the notebook itself didn't import this mini AI dot training, and that's where this get DLS function is housed. Um,
Wait, is
and
it?
it
Huh.
was for me. Let me go to my mini AI.
Wait, what? Yeah.
Check this out. Yeah, get DLS. And part of the export, it tells you where it came from, right? So this is
Right.
basically saying it came from the notebook 4, which was mini batch training. But it took me like an hour or so to figure this out earlier this week. Um,
And this is from notebook.
it originally came from the notebook
Notebook
number
11.
4 from the part 2 notebooks, right? Where it got created. It got saved to that training um, .py in the mini AI, but that wasn't one of the imported uh,
Right.
scripts in the one of the earlier code chunks. So I had to manually bring that in. And so I don't know if I ran something out of order or you know what I mean? Like, I don't know, maybe there's some user error here, but that's how I solved the problem. And it was
Okay.
this workbook and a couple others before this where also I was trying to load the same fashion MNIST data set and it wasn't
And where
working.
is that called to the get DLS at?
It's the training in mini AI under training.py.
No, where are you calling it in notebook 11?
Oh, I see. Right here. This from mini AI.training. I just imported star.
No, where are you calling it down below it where you got the
I,
error?
oh, I see. Uh, it's in this function here, the
Oh,
data loaders
inside that.
from
Huh.
DD. Because if you, let's see,
Interesting.
if I do the data loaders dot d,
I don't know why mine works.
this comes
'Cause I
from
don't
this
use it.
comes from data sets dot py, like you mentioned, but this references it references that get DLS function within that. And so
Oh.
if I just import data sets, and that was part of this, right? Like it didn't work for me. I had to actually import the training as well. So yeah, if you can figure out that mystery why it didn't work for me, or like is that get DLS in your training, or sorry, in your data sets mini AI, maybe that's why, and I just ran something in a strange order or something.
No, it does get imported inside of datasets.py in my thing. Maybe it doesn't in datasets.py in
Ah,
yours.
yeah, that might.
It's supposed to import at the top. From no, it is from training. Or that's a mystery. Oh,
You know,
did you add did you install? Did you pip
I
install the
I did
module?
not.
Okay,
So that's probably why.
that's why it's not working.
You're right.
Because those from dot training imports won't work if you
Yeah.
don't pip install locally
Yeah,
the
I would
thing.
have to actually do the mini AI or
Yeah,
point it to the right directory otherwise, right? So that's what's
yeah.
going on.
Mm.
Yeah, the way you should do it is just do the pip
Pip install.
install dash e dot thingy
Yeah.
into your whatever environment you're
Oh,
using.
good. I'm glad you were able to troubleshoot that for me. I was really
This is so
bothering me.
This is literally the second time this week that I've run into this error. One was on my own on a project I'm managing where somebody was having a problem. They did a pip install of one of these
Mm,
things, but then they made a new clone of it and they started working on it. They're like, why are my changes not working? It's like because you're not actually editing the code. It took me,
okay.
I wasn't like immediately I knew what it was. We had like investigated, but so now I'm always suspicious of that. Did you
Yeah.
install the module or no?
Yeah. So
It really
bottom
fools
line,
you because you're importing anything. Oh, it's right there. Why aren't
yes,
you? There it is.
exactly.
I see it.
Yeah.
Mm.
Reminder to
Hmm.
self to pip install mini AI. Definitely did not do that. All right. So sorry about that tangent. Just an issue that was bothering me.
No, I mean this is the kind of thing that we're here for. I think, right? My opinion. We run into these issues and
Yeah,
understand
yeah,
what's
for
going on.
sure. Yeah. Um, okay, so the initial setup here is we're starting with just a basic convolutional neural net. Um, and we use the learning rate finder to figure out what the optimal learning rate should be. And then I go back to the notebook 11 where we've loaded in the data set. Here we've defined the model, right? It's just several layers of these convolutional items where the image is smaller and smaller, essentially, with the way these things are working in sequence till you get like a 1 by 1 pixel. Um, we run that learning rate finder that we've defined earlier. And I think Jeremy kind of lands on a 0.2, makes sense here. And in the previous segment, I think I wasn't part of that session with you guys, but there's these kind of cool visualizations that he's making. And what we're showing here is what he's describing as crashing activations. Each of these are separate layers. And if you see this basically hill and then followed by like a crash, right? That's a bad sign that your training is not going to go smoothly. Uh, the activations are not learning in a stable manner. So if you see this kind of pattern, that's bad news. And we're seeing it here just with just a straight up applying like several convolutional layers. And then there's this other visualization that he has too, which is showing you like, hey, what are the means and standard deviations of my activations in the various layers? And the idea is you want a mean of 0 and a standard deviation of 1. And we're definitely not seeing that here. I mean, yes, the means kind of start low, but they spike up, and the standard deviations certainly are not hovering around 1, which is what we would want for, I guess that's a good proxy for an indication that your training is going to go smoothly, right? Your training for more epochs is actually going to have value for you potentially, right? That you're going to actually get better loss when you extrapolate to your validation set. So that's our starting point. And then back to my kind of summary slide here, summary workbook. Jeremy goes on a tangent about GPU memory. I thought this was actually kind of cool. Um, when you're running Jupyter notebooks interactively and you have a bunch of outputs, that takes up memory, and some of that might be stored on your GPU. And so, and also when you get traceback errors, that also creates issues where you could be storing things on the GPU, which is bad news when you're trying to train. And so what Jeremy does is he creates a couple he creates this function here to kind of clean out some of the stuff that's just hanging out there in memory in a Jupyter notebook. And apparently he took this from, yeah, the IPython source code and adapted it here. He doesn't really run through all the details. And then here's another function that cleans out when you have traceback errors that also takes up memory. He combines that all into this master function that he's calling clean memory. So it's applying this clean TB for the tracebacks, clean the IPython history, which we've defined up here, doing a separate garbage collect for any other memory, and then emptying the cache for CUDA. So like 4 different things together. So if you're, I think the main point here is if you're running into errors, like CUDA errors, it'd be a good idea to run this sort of function, and it might help you going forward.
I found that really useful actually, because I run into that in the past and found it so frustrating. I didn't even know about that or forgot about that IPython notebook history thing, the underscore thing. So I'm like, oh
Yeah.
I just always was restarting my kernel like a lot. You know what I mean? Like it's so frustrating, especially when you have a lot of setup and it takes some time. Like, what the heck's going on here?
Yeah, I think that's probably the only other solution, right? If you don't have something like this, you just have to restart your kernel to get everything out of there. And the other cool
Restart the
trick,
computer, just get a whole new computer, throw that one away.
that too, that would work. Speaking of yeah, random issues, this week I had a WSL Conda environment that stopped working. I had it set up to work on the GPU, right? It no longer worked on the GPU this week. And then I had a Windows-based Conda environment that previously was not working on my GPU, even though I have the CUDA stuff installed in there. This week, it was working. I don't understand how that's possible.
I don't know.
Since
I feel like I run into that kind of stuff all the time. It's just like I have no idea why these things change. Maybe it's some kind of system update change.
Yeah, but you know, I'm doing that check default device or whatever, and I'm like, I know last week this said CUDA, and now it's saying CPU. What the heck's going on? And then I found the reverse issue for my Windows Conda. And I'm running like training models, and I can see my GPU going crazy on my Windows environment, and the WSL, it's all CPU.
Huh, I'm gonna have to try that.
Pain in the butt. But historically, we've talked about this before, Ron. I seem to have better luck in general with the Linux environment.
Yeah.
With PyTorch in general, I think that's kind of
Me
the recommendation because things are finicky in Windows. So there's also this underscore trick. So if I just create something here like foo, right, and I print it out, that output stores in the Jupyter environment. And if I just hit underscore, it will pull that back up for me. And I think you can actually do double underscore. I think I probably did this before, so maybe that's why it's still showing high. Maybe that's the only thing there, but I think you can actually get numbered items too if you, I don't think I do in here. Oh, what's this? Yeah, here we go. So you can actually look at previous history of things that you've done in your Jupyter notebook. So not sure if you guys were aware of that. I was not before this video. I think that's kind of cool.
No, I mean, there's something similar that in Mathematica that I've always used, and I had no idea the notebooks had that same capability.
Yeah.
Or these notebooks.
Yeah, but that is proof that, you know, your output is
stored,
is being stored. All right, so that's the GPU stuff. Then we go into the whole initialization concept, which is kind of the key part of this lesson. It all really revolves around, you know, when you're training a deep learning model, it's all about the matrix multiplications. And if you aren't initialized properly and you're doing like you have a lot of layers to your model, you could end up in a situation where you have extremely large numbers at the end of the day, or very small numbers, right? Like something that the computer would call infinity, or in this case, nans, This is just a random example where we're starting with unit normals in a matrix and doing a bunch of random matrix multiplies together 50 times here. And, without applying adjustments, you end up with these nans because essentially you're coming up with these extremely large numbers. And if you scale some of this stuff, you may end up with a bunch of zeros. So you don't want to end up with infinity or nans, right? Or zeros. That's kind of bad news. Or near zero, or just something very, very large. That really can interfere with your training. So the idea is you want your weight matrices normalized in such a way that while you're doing these matrix multiplies, that you have a stable mean and standard deviation. And I think the ideal idea is that it's mean 0, standard deviation of 1. And so I think the first thing we talk about is this trick where you multiply the number of inputs that you have in your weight matrix by 1 over the square root of n, where the n refers to the number of your inputs. And we do it. Oh, yeah. And so we apply that here. It's kind of the same thing we looked at before, where we're doing 50 matrix multiplications, but with each, because we have 100 inputs here, and we're scaling by 1 over the square root of 100, square root of 100 is 10, 1 divided by 10 is 0.1. So we're just kind of hard coding 0.1 in here. We see that we end up with a stable end result, right? Whereas before, when we just kind of did the random initialization without that adjustment, we ended up with zeros here, or potentially, those really large numbers that we would just say are infinity, right? Or just very large. So that works when you're dealing with linear layers. And we'll see in a second that doesn't work when you have ReLUs. So we need another trick for that. Going back to my outline of the lesson, Jeremy, this is where it's always interesting, right? Because he goes very deep and then very high level as well. So he spends about like 10, 15 minutes on just basic stat stuff, like what is covariance and what is standard deviation. So we don't need to go through that.
Right.
I will spare the team of that. The 1 over square root of n trick is called Xavier Glorot, I believe, initialization. There's a paper. It's referenced in the notebook itself, so I'm not going to post it in the chat. As I mentioned, it doesn't work when you have a ReLU activation. It may not work when you have other nonlinear activations as well. I didn't really experiment, but certainly not when you have ReLUs. And I'm going back to the class notebook here, the notebook 11, scrolling down past all the basic, like here's what covariance means and correlation. Okay, so now he has an illustration, like we're doing what are we doing here? We are just doing a straight up, multiplication where we have a matrix A, 512 by 100, multiplying that by a vector that's, we'll just call it like a 100, like a column vector, right? With 100 rows. And it turns out that both X and A in this case are initialized with random unit normals. And, when you're multiplying this matrix by the vector, you could think of how you do matrix vector multiplies, right? You multiply each row by the column vector, right? And so so you're multiplying elements together and then adding them up, right? And so each element-wise product is you're multiplying two random unit normals together, right? So mean 0, variance 1, they're independent of each other. The end result is, that product is actually another unit normal random variable in this case. Right, mean 0, variance 1. That's not always the case. I was just doing a little refresher, like when you're multiplying two independent random variables together, this is the formula for it. Just from cross-validated here. But we have two independent unit normals. So a lot of these terms kind of wash out to 0, right? Expected value of X, it would be 0. Expected value of Y, 0 in this case. We have two unit normals, so variance are 1 in both cases. So so each of those element-wise multiplications, you end up with a new random variable that's also normally distributed, but we're adding up 100 of those. And so, when you add up, IID random variables, the variance kind of scales by how many things you're adding together, right? So the reason why I'm going through all this kind of to give you the intuition of why in this Xavier-Glorot adjustment, we're dividing by the square root of n, right? Because your variance scales with the number that you're adding together. So in this case, it's 100. So your variance gets multiplied by 100. So the standard deviation would be the square root of 100. So we're applying this 1 divided by square root of 100 adjustment. And that's getting us to that standard deviation of 1. That was a long-winded way of kind of describing this format that he's describing here. Does that make sense? Okay.
Yes.
Again, I've mentioned this multiple times now. When you have a ReLU, this nonlinear ReLU activation, you can't use that trick. It won't work. Jeremy kind of walks us through an example of just a basic forward pass. We have two linear layers, two weight matrices. And we're applying to each layer that the 1 over square root of n trick, but we don't have any nonlinear activations here. And so we end up with something that's like a mean of 0 and not. But if we do that same sort of forward pass, apply a ReLU to the end of the second layer, and we do a bunch of matrix multiplies, and we use that scaling trick. We do end up with a bunch of zeros here. I don't think that's good either. I can't remember all the details here, but long story short, you do not end up with a mean of 0, standard deviation of 1. So the trick here from this other paper by Keiming is to multiply by the square root of 2 over the number of inputs. So with that adjustment, we end up with a more stable result. Okay, I think that's the main point here is when you have the ReLU, you still have an unstable result when you're doing a bunch of matrix multiplies. Here, things kind of shrank to 0, and that's bad for training. With the square root of 2 additional adjustment, once we did these 50 matrix multiplies, we still have a stable result at the end of the day. That's what we're saying. I think we show kind of later on that we still don't end up with that ideal situation with the mean 0 and standard deviation of 1. Okay. Anything else? I think we walk through this example. Okay, yeah, where we do initialize the weights using, let's see. Okay, yeah, using that square root of 2 rule, we call that the the K-ming normal function. That's within the PyTorch library. Okay, cool. And we refit the fashion MNIST data set, and now we get something close to 85. We have, 84 and some change in the validation set, and we had what before? Scrolling up so I remember. Whoops. We only ran one cycle here, and the accuracy was horrible. Maybe that's because we weren't getting a stable result. Okay, so I don't know if I have a good baseline for us, but with this, that one initialization to our weight matrices, we ended up with an 84% accuracy. We see that we're still getting some crashing activations here, but it looks better than we saw before. There is still some kind of leveling out to a degree, which is what we want for all of these layers. And then we're still not achieving the means of zeros and standard deviation of 1, which we want. Okay, so now we're just looking at more stuff that we can do to improve our training. So that those techniques we just reviewed were just to the weight matrices. You also need to normalize your inputs, right, before they're fed into the neural network. That's best practice. There are different ways to do that, of course. I think we're just kind of doing the z-score version here, where we're subtracting the mean, dividing by the standard deviation. You could divide by the maximum value, things like that. But oops, I guess I didn't have to rerun the notebook here. But this is fairly straightforward. Jeremy creates just a batch transform callback, and he does this so that we can easily plug this in when we're training, because we've created these learners and these fitting functions where you can easily insert all these callbacks, right? And so he's taken this modular approach, so then now we can just say anytime we have a batch of inputs, let's just normalize it up front. Just basically take z-scores of all of our inputs. And so now we run the same model again. I think we're also doing the normalization of the weight matrices as well, in addition to the inputs. And again, we're still seeing some activation crashes, but things are leveling out a bit. Means still not 0. Standard deviations look a little bit better. Not quite 1, but they look more well behaved than we saw before. Accuracy is 84%, roughly. Not much of an improvement overall. Actually, that's slightly worse. Okay, going back to my outline. Jeremy talks about this concept general ReLU. Hadn't heard of this term before. I don't know if it's something he came up with. It kind of sounds like he did.
Yeah, it sounds like he introduced it himself.
Yeah, and so his point is that with a ReLU activation, you're never going to end up with a mean of 0 on your activations just by how the ReLU is defined. The only way that you can end up with an average of 0 in your ReLUs is if all of your outputs are just 0, which is it's generally not going to happen, right? Because all those negatives get converted to 0. Otherwise, you get a positive value. So there's nothing to offset your positive values. And so what he does is he says, well, what makes it a general ReLU is you can just subtract a value from the ReLU so that you do end up with negative values. I really, he didn't go into much detail about how he decided what he wanted to subtract from the ReLU. I guess, wouldn't that be something you could, I guess, test across multiple validation, or just run, against validation sets multiple times?
I haven't looked into it, but I find it hard to believe it makes any difference at all, because right away
Okay.
there's a bias after the multiplication. So I don't
Yeah.
think it's redundant to that. So I think it's just so it makes it nicer so you can get 0 mean or something. I don't know. For just looking at it.
Yeah. Yeah.
Visualization.
he
which is
doesn't go into
important.
much detail about it, right? He just says like you can do this, just subtract something so that you can get some negative values. He doesn't really talk about how you optimize that if you even need to. To your point, maybe it doesn't really matter, and that's why
I
there
haven't
wasn't much.
tested that, but I just don't think it can matter. But
Yeah.
I'm probably
Uh,
wrong.
the yeah, and it's again these lessons are long, so it's like you don't have a lot of time to experiment in between each of these lessons here. The other tweak he does is he does a leaky ReLU as well, so that you are getting negative values just kind of out of the box by definition because you're using the leaky
Yeah, no,
ReLU.
that is standard. I mean, not only does it give you negative things, but it makes it so the neurons don't completely die when they go to zero. They can
Yeah.
have some gradient and come back, have a chance to come back to life.
And just a point that he brings out is like there's this chiming normalization in PyTorch, uh, and you can input this argument A, where you specify like the leakiness of your ReLU.
Right.
So that's just a little call out there. Um, Implementing his general ReLU, it did seem to improve the overall result, 87%. I think we all know what a ReLU looks like. He's just kind of plotting that for us. Just going through the same steps we walked through before. Yeah, almost 87%. And you can see that things do look even more stable than those previous normalization techniques we applied. And, you know, our means are getting closer to zero. You know, some are above, some are a little below. Standard deviations aren't quite one, but they look certainly more well behaved. Just trying to see in that general ReLU function what he actually applied, what that subtraction amount was.
It was 0.4.
0.4.
Yeah, it's in when he makes the model.
Okay. Where is that though?
There it is. Oh, right. Partial activation.
Oh, sub 4. I
Curve.
see.
Yeah.
Yep, there you go. Yeah. So he just subtracted a 0.4 from the ReLU result. Cool. So we're making some progress. Going back to my outline, the next concept he talked about, I thought this one was pretty cool. Layer-wise sequential unit variance. Same kind of idea where you're trying to target that mean of 0, standard deviation of 1. But here you're just saying like, well, I can use just any kind of a random initialization that I like, anything that my heart desires there. Then you create a model, look at the first layer, see what the means and standard deviation is. If the standard deviation is too high, you can divide by that amount to get it closer to 1. If it's the mean is too high, you can subtract it, right, to get it closer to 0. And so what's cool about this approach is it's agnostic to whatever activation function you're using. Whereas that Kaiman, I pronounce that right, that normalization technique we just reviewed, the square root of 2 or 2 over n square root of that expression works for ReLUs, but I don't think that is necessarily agnostic to any type of activation function, whereas this would be. So that's pretty cool. And probably won't run through this other than he mentions like you can create a hook for this again, so that this is easy to plug into your models. It's kind of a modular approach here. And I think he got close, or I got close to an 86% accuracy when I ran using this LSUV technique. All right, maybe we'll just look at it real quick. Yeah, 86 after a few epochs. Again, like we're kind of close to 0 here. Some craziness happening early on in training, but still more stability than we saw initially when we weren't doing any sort of normalization at all. All right. We got 20 minutes left. I think I can cover most of this stuff. So then he moves on to batch normalization and layer normalization, which I guess is a more simplistic version of batch normalization. I have heard of this approach before. In fact, when I was first really learning about deep learning, I think it was through like the Coursera Andrew Ng's, deep learning.ai courses. And this is one of the things I think in his first class that he goes over is batch normalization. And so this is considered an improvement upon what we kind of just went over. Those techniques we looked at before, we normalize the inputs before training, but what happens is the distribution of weights and inputs do change during training, and that's due to something that they call internal covariate shift. And what batch normalization does is it does the normalization process during training for each mini batch. And so this is seen as an improvement. It's something that's not all that old of a technique, came out in 2015 apparently. And again, this is in the notebook that's just part of the course, so you can reference that if you want. So this is kind of interesting. The main idea is you're still subtracting means and dividing by standard deviations. So you are providing this normalization step. But then once you have that result, you're multiplying by a scaling factor and then adding a bias term. And that scaling factor and that bias term that you're applying is a learnable parameter during training. It's just another learned parameter. And apparently that is just something that, in recent history was kind of used across the board. It was almost like a universal approach, apparently, because it ended up getting good training results, smoother training, in fewer epochs, for instance. But after Jeremy goes through all this, he says, well, in today's age, right, in mid or late 2022, whenever he recorded the video, he was saying folks were actually moving away from batch and layer normalization, and that it adds complexity, maybe too much complexity. I don't know if it's an interpretability issue or what. He doesn't really get into much detail about it. It has become less fashionable. I guess is the long and short of it for batch normalization. When we ran this, it got really good accuracy though. Let's see, layer norm, about 87% accuracy. Creates this batch norm class, and I think that was a little bit better. Yeah, 87.3 versus what did I say? 86.8. Yeah, so getting closer to that 90% target that we were shooting for. There are different types of norms that are applied out in the wild. He doesn't really go into much detail. There's instance norm and group norm. Still a little confusing to me. This is a graphic that he uses to show like what are the differences between these different norms that are out there. One thing that helped me was this Medium article that compares and contrasts batch normalization and layer normalization. And so the way I am interpreting this is I'm thinking about, each of these vectors. Think of that like if we're dealing with an image, like maybe each one of these is just an image, right? Just kind of layered out in one column. And so like we have a mini batch of 3 maybe in this instance. And so with batch normalization, we'd be taking means of pixels. Think of like the upper left pixel in my image across 3 different instances in my batch, right? And so for each pixel, we're taking a mean and a standard deviation. So that's what we would be doing in batch normalization. Whereas in layer normalization, we're actually taking the norm of all of the pixel values in an image, right? For each instance. So we're doing that 3 times because we have 3 instances in our mini batch. So we're just normalizing different things. Like, I'm probably oversimplifying a little bit, but like, are we normalizing individual pixels across multiple examples, or are we normalizing across samples, right? All of the pixels in our within each within each sample of our mini batch. So two different things. At the end of the day, I think you kind of achieve kind of the same thing, right? It's smoother training. You're still trying to achieve something close to that mean of 0 and standard deviation of 1 on your activations.
Yeah.
Ron, I think you're probably, you know, the most well versed in designing these things in the real world. Do you use batch norm or any of these things on a regular basis, or when you've built these types of architectures?
I haven't been doing much actually with deep learning recently.
Hmm.
Much more likely to be using Bayesian inference these days. But when I was doing it, yeah, we definitely use batch norm and layer norm. Layer norm seems like very popular. I mean, I know it's in the transformer models.
Okay. Yeah, and I think there was a call out that layer norm is used more for NLP type stuff,
Okay.
NLP type task, and
I didn't catch
batch
that,
norm
but
was maybe more for images.
that would make sense though to me. But yeah.
Okay. Okay.
Trying to remember what we use in the graph context. I feel like we use batch norm, but I don't remember. To tell you the truth, the things kind of blend together.
Blend
after a
together, right?
while.
Yeah, for
We
sure.
definitely use one or the other.
All right, so this is kind of like the finale of initialization here. So we're applying normalization to our inputs, normalization batch norm using, now we're just using PyTorch's version of batch norm, and changing the batch, we've increased the batch size to 256. And so this is just kind of ad hoc stuff Jeremy. He starts with a higher learning rate, 0.2, runs that for a few epochs, getting close to 89%. Then he's like, okay, well, let's now fine tune this using a smaller learning rate for a couple epochs. So, you know, ad hoc, like I said, like just artistic choices he's making, and that gets him over that 90% threshold. I think in the videos he doesn't quite hit 90, but I did. Just I had a lucky bounce, right, with the random initializations. So that's pretty good. And that's it for the initializations. And then we move on to you know, tweaks to the optimization process with stochastic gradient descent. And this is, we've got about 10 minutes left. This was probably only about 20 minutes worth of the video anyway. So let me,
It was
yeah,
30
so
minutes of the video.
what, okay.
I put some timestamps in my notes, so I keep track of everything.
I definitely spent less time with this stuff, but basically, I think we all know what, you know, what the standard stochastic gradient descent looks like. We've covered this ad nauseum, I think, throughout the course series here. The one tweak that he adds, well, he makes a stochastic gradient descent class, and then he adds a regularization step to this. So basically, it's the equivalent of L2 regularization, right? Which when I think of just regular regression, that's like ridge regression. So you're taking the square of your weights, right, added to your loss term. But when you take the gradient of that, right, you're no longer looking at a squared term because the 2, right, kind of goes away. The square term, right, comes out front. You multiply by 2, but you can kind of get rid of that 2 for the purposes of optimization. And I think in the neural network deep learning world, they instead of using like when you think of ridge regression, there's a hyperparameter lambda that you see out there. Here, they use a term called weight decay. It's basically the same thing. And you can kind of play with different weight decays to get an optimal step. So he's just adding that as an extra step to the normal stochastic gradient descent process. Okay, so that's in his library that he's building. let's see, scroll down here. He defines this regularization step, and he kind of goes through some of the math of why this works. But at
But
the end,
we did do it before as well. So
yeah, at the end of the day, it's the equivalent of doing that L2 regularization. It's an extra piece that we're adding to the optimization step. And so from there, whoops, going back to my outline, he talks about momentum. I think we've talked about momentum to a degree in the past. The story here is that as you're training, you're calculating these gradients, and then as you're going through more and more batches, momentum says, okay, what was my previously calculated gradient, right? And what is my gradient for this new batch? And really, you're just taking a weighted average between what you're seeing in the current batch and what you've used previously. So it's a matter of a linear weighting, something between 0 and 1, between old and new. And of course, the old it ends up being an exponentially weighted average because it's right carrying over from batch to batch. So there's really kind of exponential decay that's going on. But it's really easy to implement, right? Because you're just applying this weighted average of, hey, what was my previous gradient? What is my new gradient? Let's take a linear weighting between the two. Going back to notebook 12 here. I think he kind of just shows you with momentum. There's like, if you use a high beta coefficient, you're not really going to follow your training data, right? You're going to get a smoother function. If you use a lower value, you're going to be closer to using what the gradient is on each batch for each batch, but you're going to be noisier. That's the point here with this graph. It's just kind of dummy data. But to actually implement gradient or momentum, excuse me, it's very easy because we're just doing a weighted average. That's the point. I don't really want to go into any more detail here. So he applies this, but I'm actually getting something slightly worse in terms of like accuracy than that 90% with some of Jeremy's tweaks. But for when you look at some of his charts, like this color dimension plot, like you don't see any of those crashing activations at all. Things are very smooth. So this is a sign that training is going well. And then as an improvement on standard momentum, there's something called RMS prop. This used to be more popular. I don't think it's as popular today. And it's similar to momentum, except instead of this batch, you're not looking at the gradient itself, you're looking at the squared of the gradient. And then you're doing a weighted average between, I think, a previous squared average, right? And the new squared average. And then if you're coming up with a really high gradient, you basically are applying this normalization term where you're dividing by the square root of this weighted average, right? So the gradient for your mini batch divided by the square root of this average of averages. Yeah, so you're not overfitting to noise, essentially, is the main story here with RMS prop. And we implement this, and I actually get slightly worse results than straight momentum, but it could be just the random bounces in initialization. But once again, according to these charts, we're getting some pretty good output here. So no crashing activations. Things look very smooth. And then final step is Atom. And, I think Atom is ubiquitous for a lot of deep learning tasks these days. What I didn't realize is that Atom is really just combining standard, momentum, and RMS prop together. So that's all it is. And the code to do this stuff, to combine both of these, is not all that complex. Instead of like one beta term, you have two beta terms, one to control standard momentum, one to control RMS prop. And Atom in this case worked better than both momentum alone or RMS prop alone. And I don't think we didn't actually print out any of these.
That's where you ended it, yeah.
But yeah, so
He answered some question about batch size at that point. That was about it.
Yep. And so that's where we ended. Like I said, Atom is I think and a lot of the material I've reviewed, that's kind of the default optimizer that you're using. I don't know, there's maybe something better these days, but my knowledge is probably dated by a couple years anyway, but Atom's a pretty common one.
I think it's still the default.
All right. And so that was a lot of different topics, a lot of ground.
Yeah, it really was.
We covered. And it's funny because
Like
we're
we
going
say
through all
that
the
every week.
yeah.
Yeah, and it gets more, it seems like. What's next week gonna be like?
And we've learned all this stuff, and it was like, 90% of it we'll no longer ever use. Right? It's like, well, here's what you want to do these days, but for historical reasons, this is interesting. And obviously, research builds off of previous research. So it is very interesting, but it's a lot.
I like what Mallory says about things like this. He says sometimes you just gotta let this stuff wash over you, and then you'll come back to it later. You'll know what it is, but you won't
Yes.
realize it completely. Just let it wash over you.
Yeah.
That's what
Yeah.
I've been doing the last 3 meetings.
Yeah.
All right. So
Thank you
that's it
much.
for this week.
I'll plan to present next week. Yeah.